What's up, guys? We originally learned what the natural log of -1 is, but now, what if we expand that even more and we look at the natural log of 2 plus 3i? What? Well, we're going to find what the natural log of a complex number is today. Okay? Alright, let's get right into it. Let's just do a quick little recap. So, first, we derived this equation right here using the Maclaurin series of e to the x. And then we use that information to take the and we see that using an extension of Euler's identity, we can see that e to the I pi plus 2k pi, where k is an integer, is equal to -1. And we could take the natural log of both sides, and we can see that 2k plus 1 times I pi, where k is in any integer, is equal to the natural log of -1, right? And so we use that to figure out that the natural log of -x is just the natural log of -1 times x. And so we use the property of logs to separate this and derive our expression for the natural log of a negative number, where you see that the natural log of a negative number is equal to the natural log of the number plus 2k plus 1 times I pi, where k is any integer. All right. Okay. So there. That's just what we went over in the last video. But before we get into all this, we're going to have to go over some terms we need in the complex plane, and we need to understand how stuff works in the complex plane. So first, we need to learn how complex numbers work in the complex plane. So I think we all know how the complex plane works. Our vertical axis will be our imaginary line, and our horizontal axis will be our real number line. So say we want to graph the complex number 2 plus 3i. We go to the right 2 in the real number line and up 3 in the imaginary line. And when we graph points in the complex plane, we can see that it very much resembles a vector, and the way that we write complex numbers actually splits up its components just like a vector, where 2 is our horizontal component and 3 is our vertical component. So there, we've established that complex numbers are vectors. All right. Well, that's the first thing we need to understand about the complex plane. Now, let's look at the modulus. The modulus is something that is an important factor when we're going to find the natural log complex number. So we can say that the modulus is the magnitude of our complex number. And the formula for the magnitude is the square root of our x component squared plus our y component squared, because that's basically the Pythagorean theorem, right? So using this, we can find the modulus of a complex number by finding its magnitude. So say we have this complex number 2 plus 3i. So we're going to find the magnitude, or the modulus, we're going to find its magnitude, and we can do that by doing the square root of 2 squared plus 3 squared, and we get that that's the square root of 4 plus 9. And when we add that up, we get that the modulus of 2 plus 3i is the square root of 13. Easy, right? But yeah, that's just essentially how a modulus works. The way this is because complex numbers work very similar to vectors in the complex plane. But yeah, now here's where things get a little tricky. We're going to learn what an argument is. So an argument is the angle that our vector, or a complex number, makes with the real positive x-axis. That is how we define what an argument is. So when we check in the first quadrant, theta is our argument, okay? And to find theta, we can split up our vector into our x and y components, and we can set up a triangle. So let's do that. We set up this triangle, and now we can solve for theta by using trig. We can say that the tangent of theta is equal to b over a, and we could solve for theta and get that theta is equal to the arctangent of b over a. So now we found the argument for a complex number in the first quadrant, which is just the inverse tangent of b over a. So let's run through a quick example. Let's find the argument of 2 plus 3i, and so we can just do that by doing the inverse tangent of 3 over 2, or b over a, where b is 3 and a is 2. And we see that the argument of 2 plus 3i is approximately 0.983 radians. Make sure your calculator is in radian mode. So let's look at our second quadrant now. This is where things get a little complicated. So theta is our argument, right? But gamma here is the angle that we make, or the angle that we find, that our horizontal and vertical components of our vector makes with our negative x-axis. Or in other words, this is really the only angle we can actually find using given the information of our vector or our complex number. So let's split our components up into a triangle, and let's solve for gamma. Just like in the first quadrant, we can use trig to figure out that gamma is equal to the inverse tangent of b over a. So now, to find it, we know that the argument of our vector is theta. And so actually what we can do is we can do pi, because pi is technically the first and second quadrant. It's a rotation to the real positive x-axis, to the negative x-axis. And so what we can actually do is we can find theta by doing gamma plus pi. Because we know since gamma is in the second quadrant, it's going to yield a negative number. And so we can actually add pi to find our argument. So let's do a quick example with that. So let's say we want to find the argument of negative 2 plus 3i. So what we can do is the inverse tangent of 3 over negative 2, and then we can add pi to that. And we see that gives us approximately 2.16 radians. All right, let's look at the third quadrant now. So the third quadrant is where things start to get very similar to our second quadrant. Well, so this is why I didn't really make a graph for it, but it's essentially the same as the second quadrant, but with a little bit more steps. So alpha is going to be the angle we could find between the vector and the negative axis, because that's the only angle we can really find given the information of the complex number. So what we can say is the argument of our vector is the inverse tangent minus pi. Because now what's closer to us is if we go 180 through the fourth quadrant to the real positive x-axis. So we can actually find the angle, or the angular distance needed to reach the positive real axis through the fourth quadrant. And we can actually do that by taking our inverse tangent of b over a using our triangles, and we can subtract pi from that. And so we can figure out that the argument of z is the inverse tangent of b over a minus pi. And so now let's do an example where we can find the argument of -2 plus -3i, and we can do that by saying that's equal to the inverse tangent of -3 over -2, and then we can subtract pi from that. And we see that our argument is actually approximately -2.16 radians. So now let's look at quadrant 4. Quadrant 4, it's going to be the exact same basis as our first quadrant. So all we're just going to do is take the argument of the inverse tangent of b over a. Because now, since we're closer to the real axis through the fourth quadrant, we could just find the angle between the vector and the real axis instead of going all the way back to our first quadrant and by subtracting 2 pi. So let's do an example. Let's find the argument of 2 plus -3i. We can say that's equal to the inverse tangent of -3 over 2. And we see that the argument of 2 plus -3i is approximately -0.983 radians. All right, well, that is the two terms that we are going to need to know to figure out how to find the natural log of a complex number. Figure out how to derive the polar form of a complex number. So in the polar plane, we can define cosine and sine as both of these fractions, where we can say that x divided by our r, some constant r, is equal to cosine of theta, and y divided that same constant r is equal to sine of theta. So we can do some rearranging, and we can see that x is equal to r cosine theta, and y is equal to r sine theta. Okay? So now, let's take our complex number, or the form of a complex number. We know that a complex number can be defined as an x and y component, where our real part is our x component and our imaginary part is our y component. So we can actually say that z is equal to x plus iy, because we are now just splitting up, we are just showing the components of our complex number. So now what we can do is we can plug in our definitions for our chords in the polar plane, and we can see that z is equal to r cosine of theta plus I r sine of theta. So now what we can do is we can actually take that r out, and that looks kind of familiar, doesn't it? Because that is actually the formula we derived in the first video. And so we actually can find the polar form of a complex number. We can say it's actually equal to r times e to the I theta. And so now this will be important when we are going to be trying to find the natural log of a complex number. And we know that r will be our modulus, okay? And we went over what our modulus was. It was our magnitude, and we can find the magnitude using the Pythagorean theorem, which is the square root of a squared plus b squared, or the x component squared plus the y component squared, right? And I'm actually running out of space, so I'm actually going to move these lines a little bit up. Just give me a moment. But yeah, we know that r is equal to our magnitude. It's our modulus of our complex number. And we know that theta is actually, we actually know that theta is actually our argument that we went over. So we can actually say that the polar form of a complex number is the modulus of our complex number times e to the I times the argument of our number, or our complex number at that. So there, we found the polar form of a complex number. So now we found the polar form of a complex number, and now finally we made it to what this whole entire video is about. We can now find the natural log of a complex number, so let's get into it. We know that the natural log of any complex number following a plus bi is going to be equal to the natural log of the modulus, or the magnitude of our complex number, times e to the I times the argument of our complex number. So we take the natural log of both sides, right? and we see that the natural log of a plus bi will equal to the natural log of the magnitude of a plus bi. That will be a real number, and it's going to be plus the natural log of e to the I times the argument of a plus bi. But now we can actually now complete the natural log, because we know that taking the natural log of e to the power something is just going to yield that exact number, because natural log is just the logarithm base e. So we actually know now the natural log of a plus bi is equal to the natural log of the magnitude of a plus bi, which is a real number, plus I times the argument of a plus bi. But one thing we have to recognize is every 2 pi radians, the angle cycles or is equivalent. So we can say that the natural log of a plus bi is equal to the natural log of the magnitude of a plus bi, or the modulus, plus I times the argument of a plus bi, plus 2 pi ki, where k is an integer. So now we can just do some simplifying and some grouping, and we can now completely define the natural log of a plus bi as the natural log of the modulus or the magnitude of a plus bi plus the argument of a plus bi plus 2 pi k times I, where k is any integer. Now, would you look at that? We found the natural log of a complex number. Look how big we jumped. We jumped from the natural log of -1 and just a normal negative number to an entirely new plane, the complex plane. All right. I was kind of too lazy to render this last part, but I just wanted to thank you guys for watching. This video took me way too long to make. It was over like 500 codes in Mainum, which is like agonizing, but it was worth it. All right. Well, thank you for watching, and goodbye.